We are going to see about Bohr theory of hydrogen atom and Compton effect. Bohr retained the essential features of Rutherford model. In order to account for the stability of an atom, he introduced the concept is known as stationary or non-radiating orbits. According to Bohr, an atom consists of positively charged nucleus which is responsible for almost the entire mass of an atom, and the electrons revolve around the nucleus in certain permitted circular orbits of definite radii. The permitted orbits are those for which the angular momentum of an electron is an integral multiple of h by 2 pi, where h is Planck's constant. M is mass and u is velocity of an electron in a permitted orbit of radius r. L is equal to mu r, which will be equal to n of h by 2 pi, where n is equal to 1, 2, 3. Then L is nothing but angular momentum and n is number of orbits. The n is an integer called as principal quantum number. This equation is known as Bohr quantization postulate. When electrons move in a permitted discrete orbits, they do not radiate energy. Such orbits are called as stationary or non-radiating orbits. Bohr overcome Rutherford's difficulty to account for stability of an atom. The energy is radiated when an electron jumps from higher to lower orbit, and the energy is absorbed when it jumps from lower energy level to higher energy level of an orbit. If EI and EF are the energies associated with the orbits of principal quantum numbers Ni and Nf, here Ni is less than Nf. The frequency of the radiation emitted is given by h nu is equal to delta E, that is energy difference, which will be equal to EF minus EI. This equation is known as Bohr frequency condition. Let us now calculate the energy of electron in Bohr hydrogen atom. Let the charge of the nucleus be plus Ze. The electron with charge minus E revolves around the nucleus of radius r with velocity u. The electrostatic force of attraction between the nucleus and the electron is given by Fe is equal to 1 by 4 pi epsilon naught Ze squared by r squared. The centripetal force Fc acquired by an electron is given by Fc is equal to mu squared by r. Since the electrostatic force of attraction between the nucleus and the electron provides the necessary force, hence for the stable circular motion, Fe is equal to Fc, that is electrostatic forces of attraction will be equal to centripetal force, that is 1 by 4 pi epsilon naught Ze squared by r squared is equal to mu squared by r, where mu squared is equal to 1 by 4 pi epsilon naught Ze squared by r. According to Bohr quantization condition, L is equal to mu r, which will be equal to nh by 2 pi, or u equal to nh by 2 pi mr. Substituting this value in equation 3, nh by 2 pi m r squared is equal to 1 by 4 pi epsilon naught Ze squared r. Hence, the radius Rn of nth orbit is given by r is equal to Rn, which will be equal to 4 pi epsilon naught n squared h squared divided by 4 pi square Z m e squared. By substituting the values and rearranging the above equation gives this equation, and we see that the radii of stationary orbits are directly proportional to the square of principal quantum number n. The Bohr's radius is defined as R1 is equal to A naught, that is 4 pi epsilon naught by h square is equal to 4 pi square Z m e squared. Velocity of the electron, substituting the value of 4 from equation 4 into equation 3, we obtain u is equal to un, that is n h by 2 pi m of 1 by 4 pi epsilon naught 4 pi Z m e squared by n square h squared. After cancelling the common factors, that is nh in the numerator and nh in the denominator, 4 pi and 4 pi in numerator and denominator, we will get 1 by 4 pi epsilon naught 2 pi Z e squared by nh. If c is the velocity of light, and equation 7 can be rewritten as un is equal to 1 by 4 pi epsilon naught 2 pi z e squared by ch, that is c by n. This factor is a constant and it is called as the fine structure constant alpha. Its value is found to be 1 by 137 since z is equal to 1 for hydrogen atom and hence n is equal to 1. Un by c is equal to alpha by 1, which will be equal to 1 by 137. So we see that the velocity of an electron in the first orbit is equal to 1 by 137th of velocity of light. And we can calculate the energy of an electron also, and Ek and Ep be the kinetic energy and potential energy of an electron in nth orbit, and then the total energy will be equal to Ek plus Ep, that will be equal to kinetic energy and potential energy of an electron, that is 1 by mu square minus z e square by 4 pi epsilon naught r. We will get Ek is equal to 1 by 4 pi epsilon naught z e square by 2r. Then E is equal to 1 by 4 pi epsilon naught z e square by 2r minus 1 by 4 pi epsilon naught z e square by r. We can take 1 by 4 pi epsilon naught and z e squared as a common factor, and we will get 1 by 2r minus 1 by r, and we will get minus 1 by 4 pi epsilon naught z e squared by 2r as a energy factor. Then we are going to see about Compton effect. Compton found that if monochromatic X-rays, that is X-rays having one particular wavelength, are allowed to fall on a carbon or some other light element, the scattered X-rays have wavelength larger than the incident rays. So the scattered rays have lower frequency, that is lower energy than the incident rays. So scattering is caused by the electrons, and it is evident that some interactions between X-rays and electrons takes place, and this has a result in decrease in energy of the former one. So this decrease in energy or increase in wavelength of X-rays after scattering from the surface of an object is known as Compton effect. And applying law of conservation of momentum and assuming X-rays to consist of photons each to h nu, Compton showed that delta lambda will be equal to 2h by mc divided by sin square theta by 2, where delta lambda will be the increase in wavelength produced by collision, which is called as Compton shift, and m the rest mass of an electron, c velocity of the light, and theta will be the angle between the incident ray and the scattered X-ray. According to this equation, Compton shift is independent of the wavelength of incident radiation, and the values of Compton shift is obtained from the above equation by substituting the known value of Planck's constant, velocity, mass, and theta, that is angle between the incident and the scattered X-ray. For this discovery in 1927, Compton received Nobel Prize. So the Compton effect provides good illustration of uncertainty principle. Suppose X-rays are used to measure the position and momentum of an electron. As a result, mutual interaction of X-rays and the electron increases the wavelength and decreases frequency or energy of the X-ray. Energy is transferred to the electron, and therefore the momentum of electron changed. The momentum of electron cannot be determined with certainty. Compton effect also provides evidence for corpuscular or photon nature of the radiation. So equation 1 can be rewritten as delta lambda equal to lambda dash minus lambda, which will be equal to h by mc 1 minus cos theta, lambda dash a scattered X-ray, which is greater than lambda for incident X-ray, and the wavelength shift independent of nature of substance and the wavelength of incident X-rays, and it depends only on the scattering angle. We have two cases according to the theta value. If theta is equal to 0 degree, the scattered radiation is parallel to the incident radiation. In this case, we are having cos 0 as 1, so that delta lambda will be also equal to 0. No wavelength shift was takes place. And in case 2, theta equal to 90 degree, that is the scattered radiation is perpendicular to the incident radiation, and cos 90 will be equal to 0, so that delta lambda will be equal to h by mc. We will have the value 0.0242 Armstrong or 2.42 picometer. This referred as Compton wavelength. In case 3, theta is equal to 180 degree, that is the radiation scattered in a direction opposite to the incident radiation. If we substitute this value, cos 180 will be -1, so that delta lambda will be equal to 2h by mc, that will be equal to 0.0484 Armstrong, then it will be equal to 4.84 picometer, that is twice the Compton wavelength which we have predicted already. Thank you.